Sizing electrical service for residential homes involves several key considerations. Firstly, service sizing. A 1500 square foot home is likely to require a 150 amp service, while the 2200 square foot home may require a 200 amp service. It is important to consider the potential future load growth in the homes. Secondly, feeder sizing. You will need to determine the voltage drop from the utility meter to the homes. Use the National Electrical Code, NEC, Table 310.15. B16 to select the appropriate conductor size based on the allowable voltage drop, typically 3%. For a 700-foot run and a 3% voltage drop, the following conductors may be required. For a 150 amp service, use number 4 AWG copper or number 2 AWG aluminum. For 200 amp service, use number 2 AWG copper or number 1 AWG aluminum. Thirdly, bump and boost transformers. Bump and boost transformers can be used to increase the voltage at the end of the feeder run to compensate for voltage drop. However, this is not typically recommended for residential service due to the increased cost and potential for transformer failure. A recommendation would be to provide a 150 amp service to the 1500 square foot home and a 200 amp service to the 2200 square foot home. Use the appropriate conductor sizes to maintain acceptable voltage drop. Consider installing a surge protector at each meter to protect the homes from voltage spikes. The utility company may have specific requirements for the installation. It is important to obtain a permit from the local electrical authority before starting the project. Hire qualified electricians to perform the work to ensure safety and compliance with codes. It is crucial to accurately calculate the expected load for each dwelling to avoid undersizing the service, which could lead to nuisance tripping of breakers or an inability to power all necessary appliances and equipment. Oversizing, on the other hand, results in unnecessary expense for materials and installation. The NEC provides guidelines for calculating service loads in Article 220. These calculations take into account the square footage of the dwelling, the number and type of appliances, and other factors that contribute to electrical demand. For example, general lighting loads are calculated based on the square footage, with the demand factor applied to account for the fact that not all lights will be on simultaneously. Small appliance circuits, such as those serving kitchen countertops, are calculated at 1500 volt amps each. Fixed appliances, such as ranges, ovens, and dryers, are calculated based on their nameplate ratings, with demand factors applied based on the number of appliances. Heating and air conditioning loads are calculated based on the larger of the two, with demand factors applied in some cases. Once the total calculated load is determined, the service size is selected based on the calculated load, taking into account any applicable demand factors. It is important to consult with the local utility company to determine their specific requirements for service sizing and metering. Utility companies often have their own rules and regulations regarding service entrances, grounding, and other aspects of the electrical installation. These requirements may differ from the NEC, so it is essential to comply with both the NEC and the utility company's requirements. Selecting the appropriate conductor size for the feeder is crucial to ensure that the voltage drop remains within acceptable limits. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the beginning due to the resistance of the conductor. Excessive voltage drop can cause appliances and equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop for feeders should not exceed 3%. To calculate the voltage drop, you need to know the length of the feeder, the current flowing through the feeder, and the resistance of the conductor. The resistance of the conductor depends on the material, size, and temperature of the conductor. The NEC provides tables of conductor resistance in Chapter 9. Once you have calculated the voltage drop, you can determine whether the conductor size is adequate. If the voltage drop exceeds 3%, you will need to increase the conductor size or reduce the length of the feeder. In addition to voltage drop, you also need to consider the ampacity of the conductor. Ampacity is the maximum current that a conductor can carry without exceeding its temperature rating. The NEC provides tables of conductor ampacity in Table 310.15. B16. The ampacity of the conductor must be greater than or equal to the calculated load. If the ampacity is too low, the conductor will overheat, which can damage the insulation and create a fire hazard. When selecting conductors for underground installations, you need to use conductors that are specifically rated for direct burial. Direct burial conductors have insulation that is resistant to moisture, chemicals, and physical damage. The NEC requires that direct burial conductors be buried at a minimum depth, which depends on the voltage and the type of installation. You also need to protect the conductors from physical damage by encasing them in conduit or other protective material. Using bump and boost transformers to compensate for voltage drop is generally not recommended for residential services due to the cost and complexity of the installation. Bump and boost transformers are typically used in commercial and industrial applications where voltage drop is a more significant concern. However, if you are unable to reduce the voltage drop by increasing the conductor size or reducing the length of the feeder, you may need to consider using a bump and boost transformer. If you decide to use a bump and boost transformer, you need to select a transformer that is properly sized for the load. The transformer should be installed in a weatherproof enclosure and should be protected by an overcurrent device. Surge protection is an important consideration for all electrical installations, especially in areas that are prone to lightning strikes or power surges. Surge protectors protect appliances and equipment from damage caused by voltage spikes. Surge protectors are typically installed at the service entrance and at individual branch circuits. The NEC requires that surge protective devices, SPDs, be installed in certain types of occupancies, such as dwelling units. It is important to select a surge protector that is properly rated for the voltage and current of the electrical system. The surge protector should also be listed by a recognized testing laboratory, such as Underwriters Laboratories, UL. Obtaining a permit from the local electrical authority is essential before starting any electrical work. The permit ensures that the work is performed in accordance with the NEC and local codes. The electrical authority will typically inspect the work to ensure that it is done safely and correctly. Hiring qualified electricians to perform the work is crucial to ensure that the electrical installation is safe and compliant with codes. Qualified electricians have the knowledge and experience to properly size the service, select the appropriate conductors, and install all electrical equipment. They also understand the NEC and local codes and can ensure that the installation meets all requirements. In addition to the NEC, there may be other codes and standards that apply to the electrical installation. These codes and standards may be adopted by the local jurisdiction or by the utility company. It is important to be familiar with all applicable codes and standards before starting the work. Grounding is a critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people from electric shock. The NEC requires that all electrical systems be properly grounded. The grounding system consists of a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is typically a metal rod or pipe that is driven into the ground. The grounding electrode conductor connects the grounding electrode to the service equipment. The equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system. Bonding is another important aspect of electrical safety. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. Bonding helps to prevent voltage differences between metal parts, which can cause electric shock. The NEC requires that all metal parts of the electrical system be properly bonded. Arc fault circuit interrupters of size are devices that protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between two conductors, creating heat that can ignite nearby materials. ASIs are typically installed on branch circuits that serve bedrooms and other areas where arcing faults are more likely to occur. The NEC requires that ASIs be installed in certain types of occupancies, such as dwelling units. Ground fault circuit interrupters, GFCIs, are devices that protect against electric shock. GFCIs detect ground faults, which occur when electricity leaks to ground. GFCIs quickly interrupt the circuit when a ground fault is detected, preventing electric shock. GFCIs are typically installed in bathrooms, kitchens, and other areas where there is a risk of electric shock. The NEC requires that GFCIs be installed in certain types of occupancies, such as dwelling units. Smoke detectors are devices that detect smoke and sound an alarm. Smoke detectors are essential for fire safety. The NEC requires that smoke detectors be installed in all dwelling units. Carbon monoxide detectors are devices that detect carbon monoxide, a colorless, odorless gas that can be deadly. Carbon monoxide is produced by burning fuels, such as natural gas, propane, and wood. The NEC requires that carbon monoxide detectors be installed in dwelling units that have fuel-burning appliances or attached garages. Proper wiring methods are essential for electrical safety. The NEC specifies the types of wiring methods that are allowed for different applications. Wiring methods include conduit, cable, and surface raceways. It is important to select the appropriate wiring method for the application and to install it properly. Overcurrent protection is another important aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, protect against overloads and short circuits. Overloads occur when too much current flows through a circuit, causing the conductors to overheat. Short circuits occur when electricity flows directly from one conductor to another, bypassing the load. Overcurrent protection devices interrupt the circuit when an overload or short circuit is detected, preventing damage to the electrical system and reducing the risk of fire. Proper labeling is essential for electrical safety. All electrical equipment should be properly labeled to identify its function and voltage. Panel boards should be labeled to identify the circuits that they serve. Labels should be clear, concise, and easy to read. Electrical safety is a shared responsibility. Everyone should be aware of the hazards of electricity and take steps to protect themselves and others. Electrical work should only be performed by qualified electricians. If you are not qualified to perform electrical work, you should hire a qualified electrician to do it for you. It is important to keep electrical equipment in good repair. Damaged or worn electrical equipment can be a safety hazard. If you notice any damage to electrical equipment, you should have it repaired or replaced immediately. It is also important to use electrical equipment safely. Follow the manufacturer's instructions for the safe use of electrical equipment. Do not overload circuits or extension cords. Do not use electrical equipment in wet or damp locations. Do not touch electrical equipment with wet hands. If you have any questions about electrical safety, you should contact a qualified electrician or your local electrical authority. Remember that electrical work can be dangerous, so it is always best to err on the side of caution. Following these guidelines will help to ensure that the electrical installation is safe, reliable, and compliant with codes. This comprehensive approach covers not only the immediate electrical needs but also anticipates future requirements and prioritizes safety.